Hi there. So today we're going to be going over complex problems using molar mass, and these problems will use moles, the empirical formula, the molecular formula, and standard temperature and pressure. So our first problem is this. Biochemists have created an organic or carbon-containing molecule, which they know from spectroscopy contains carbon, hydrogen, and nitrogen. These chemists typically measure out their elements before reactions, but they asked the high school intern to do it. He forgot to measure it, and they need to know what molecule he created. To create it, they know he combined 1.89 moles of carbon dioxide, 0.94 moles of nitrogen in the atmosphere at STP. However, he also used hydrogen that was kept in a perfectly spherical balloon at STP. Luckily, from previous experiments, chemists know that the radius of the balloon was 1.705 decimeters. They were also able to calculate the molecular mass of the compound through mass spectroscopy as 135.15 grams per mole. What is the molecular formula, empirical formula, and percent composition of this compound? And there's extra credit, well, not really, if you find the common IUPAC names, which I will reveal in the description of this video. So, what do we know? Well, we know we're going to have some kind of molecule that's some sort of carbon, hydrogen, and nitrogen of some variety, something like this. And we also know that the chemical formula for this is going to look something like CO2 plus N2, because remember this is nitrogen in the atmosphere, and nitrogen is diatomic, and H2, which is also diatomic because hydrogen is diatomic. And this is going to yield our molecule plus some number of O2. Keep in mind that this equation is not balanced because we don't even know what our molecule is. Now you might be wondering, well, why is there a random O2 hanging out? Why isn't that a part of the molecule? Well, remember in the problem they told us right here that through spectroscopy, chemists have found out that it contains carbon, hydrogen, and nitrogen, but no oxygen. So we're going to assume that the oxygen has left in some other form, probably as oxygen in the atmosphere. So the first step for this problem is going to be to get moles of the pure elements. Now remember, our molecule is a carbon, nitrogen, and hydrogen type molecule. Well, not type, like that. Those are the elements that it combined that is in it. So we're going to need to find the moles of carbon, the moles of nitrogen, and the moles of hydrogen that were combined. So let's start with carbon. So we know the carbon came from carbon dioxide, which is CO2. And we know that he had 1.89 moles of carbon dioxide. Well, that's great, but we need to get moles of carbon by itself. So we know that for 1 mole of CO2, there is going to be 1 mole of carbon. Now I might be wondering, how do I know that? Well, this number here is the same as the subscript for the carbon in this molecule. And this will become more obvious when we do nitrogen and hydrogen. But just know it comes from the subscript for this. If we were trying to calculate moles of oxygen, which we're not because it's irrelevant to this problem, but if we were trying to do that, we would do 2 moles of oxygen if we were trying to do that. Now for this, 1.84, this is 1.89 times 1 is just 1.89 moles. So we have 1.89 moles of carbon. Now, the next element that was given to us was nitrogen in the atmosphere at STP. But it turns out we don't actually need to worry about this. This is kind of irrelevant for this. It will come in relevant for the hydrogen, however. So let's say we have, well, let's not say, the problem gave it to us, 1.94 moles of nitrogen. Well, that's it, we're done, right? Well, no. Remember, this is nitrogen in the atmosphere, so this is N2, because nitrogen is diatomic. So now we know that for 1 mole of N2, there will be 2 moles of nitrogen. And now it's more obvious here. We have our 2 here, and this 2 came straight from the subscript 2 for nitrogen, and the subscript 2 for nitrogen here, because this is the same thing. And that's where it comes from, because we're trying to find moles of nitrogen this time. And this is equal, this is going to be equal to 1.88 moles of nitrogen. Well, that's great and all, but now we need hydrogen. Now for hydrogen, all we know is that it was in a balloon with a radius of 1.705 decimeters. Well, how do we get moles from that? Well, we also know that the gas was at STP. So there is a property of gases where a mole of a gas will at STP will fill up an area of exactly 22.4 liters. And remember, liter is also a decimeter cubed. So all we need to do is find the volume of the balloon, and then from that volume, we can get the number of moles of hydrogen gas. Well, we know that there are, for the volume of a sphere, so volume of sphere, so volume of a sphere is equal to 4/3 pi r cubed, where r is the radius. Now, we were given the radius, which is 1.705 decimeters, so we know that the volume of our balloon is equal to 4/3 pi times 1.705, that's right. 705 decimeters. Now, notice that we're cubing this, so the decimeters becomes decimeters cubed, becoming volume, which is why this formula works. So, well, not just that, but the units become correct automatically. So 1.705 cubed, plugging it into a calculator, we get our volume is equal to 20.761644493 and on, right? And of course, it's decimeters cubed. But we need to take into account sig figs, and there are 4 sig figs here. So we are going to simply round this off to 4 significant figures because it's multiplication. So we know we have a volume of 20.76 decimeters cubed. But remember, a decimeter cubed is just a liter. So we have that many liters of hydrogen gas in the atmosphere. So which is H2. So now, with our 20.76 liters of H2, we can divide this by 22.4 liters per mole of gas. So this is liters H2, but this would work for all gases. So our liters H2 cancel, and we're left with moles. But we don't want moles of H2, we want moles of hydrogen by itself. So for 1 mole of H2, there are 2 moles of hydrogen. And remember, that's because the subscript for hydrogen in this molecule is H2. And if we just simply plug this into a calculator, so 20.76 times 1 over 22.4 times 2 over 1, we get a value of, well, it's a repeating decimal place, but since there's 4 sig figs, I'm going to round this off to 4 sig figs. So this is 1.854 moles of hydrogen. Now, we have our moles hydrogen, our moles carbon, and our moles nitrogen. So it's time to figure out the empirical formula. Now, the empirical formula is pretty easy to figure out from here. We have our carbon, and we write down how many moles we got for carbon, which, if I'm not mistaken, is 1.89. So carbon is 1.89. And then we have our hydrogen, which we know is 1.854. And we have our nitrogen, which is a 1.88. Now, what we do is we divide each of these subscripts by the smallest subscript. And here the smallest value is hydrogen's at 1.854. So we divide all of these. Actually, I'm going to use a different color. We're going to divide all of these by 1.854. And then we will get the actual subscripts for our formula. So if we do this, we will get carbons is 1.02, hydrogen is just 1, and nitrogen is 1.88 divided by 1.854. And this gives you 1.01. Oh, sorry, this is 1.54, not 1.84, 1.854. And then we can just round these off so that this becomes our final answer for our empirical formula of carbon 1, hydrogen 1, and nitrogen 1. So CHN. So this is our empirical formula right here. Now let's calculate our percent masses. So we have our carbon, our hydrogen, and our nitrogen in our formula. Now there's one of each of these, so 1, 1, 1. The atomic mass of carbon is 12.01 grams per mole. The molar mass of hydrogen is 1.01 grams per mole. And the molar mass of nitrogen is 14.01 grams per mole. Now, multiplying these, we're going to get, well, believe it or not, multiplying by 1, we're just going to get these same weights again. So it's just 12.01, 1.01, and 14.01 grams per mole. Grams per mole, and grams per mole. Never forget your units because that is an easy way to lose points. So adding these up, we're going to get, sorry, I'm adding this in my head. So 27.03 grams per mole. Well, you might be like, well, why did we calculate that? They gave us our molecular mass. Well, remember, this molecular mass of 135.15 is not the same as the empirical mass. And since we're using the values from the empirical formula here, like the 1, 1, and 1, we have to then calculate our empirical mass. Now, if we were to just go straight to the molecular formula and calculate it from there, then yes, we could use that molecular mass that they gave us. Now, the next step is to divide all of these by this value down here. So 27.03 0.03 grams per mole. And this is the same thing all the way down. And then what we're going to do is we're going to multiply all of these by 100%. And you will notice that actually here, the units, they cancel out when you divide. So the grams per mole will actually cancel out. Oops. Make that better. And then we can multiply all of these, or not divide, multiply all of these by 100%. And then what you would do after that would just be plug it into a calculator, essentially, which is relatively simple. And then we can actually check our work after we do that, and I'll show you how. But 12.01 times divided by 27.03 times 100 is going to give us a percent mass for carbon of 44.43. With hydrogen it's just 1.01. And that's going to give us a percent mass of 3.74%. These are percent, sorry. And for nitrogen, it's 14.01 divided by 27.3 times 100%. And that will give us 51.83%. And we can add these together to make sure that they add up to 100% or close to it. So if we add this, 51.83, we actually get exactly 100%. But if you're like 99.999 or 99.8 or 100.2 or something like that, then it's safe to assume that you're close, or well, close to right. Well, basically right. But if you're getting something like 85 or like a 95% or anything lower, or 105 and anything up beyond that, that starts to become a bit of an issue. So we have our percent mass here. So these are for carbon, hydrogen, and nitrogen. Now, how do we find our molecular formula? Well, remember we calculated our empirical mass here, and they gave us our molecular mass. So what we're going to do is we're going to calculate something called N. And N is simply equal to the molecular mass over your empirical mass. And remember that your molecular mass should always be bigger or the same as your empirical mass. If your empirical mass is bigger than your molecular mass, you've messed up somewhere and you need to go back. So for this, again, we can just plug in values. So from the start, we know that the mass is, this is actually an error. This is supposed to be 150.15. 150.15 grams per mole. So 150 point, sorry, 15? Yeah, 15. 0.15 over our mass here, 127.03. And if we do that, it gives us, this was actually, the molecular mass up there was actually right. Okay, what is going on right now? Okay, right. Sorry, my bad. This is 135.15 grams per mole. 135.15 grams per mole. And this is going to be over an empirical mass of 27.03 grams per mole. And you can see that the units cancel out, and this is just a number, so this is going to be equal to 7.03. This is equal to exactly 5. But in most cases, you will get something like 5.001 or 5.2 or like 4.8, something like that. But n must always be a whole number, so just round to the nearest whole number. If it's like 5.5, like when I accidentally put in 150.15, I think that I made an error. When you do that, I got 5.5, which just showed me that I was wrong, and it was 135.15 for our molecular mass. So now what we need to do is we need to take our n, so n times our empirical formula, which you remember was CHN. CHN. And we know that our n was a value of 5, so 5 times our CHN. And this 5 will actually distribute to the subscripts. So what happens is this becomes C5, H5, and N5. So does anyone recognize what that is? Well, for those of us who are biology nerds, we will recognize it as adenine, which is one of the bases in DNA. So this right here is adenine. And its IUPAC name is a lot more complicated. The IUPAC name is actually 7H purine 6 amine. And that concludes this video. Thank you for watching. I know it was pretty long, but I hope you learned how to do some of these problems.